Welcome to Teolumen Insights, where we reveal the hidden forces that shape the way you live and show you how to use them to create real transformation and supercharge your health, mindset, and daily life. Here are your hosts, Emma Greenwood and Nathan Sinclaire.
Welcome back to Teolumen Insights. You're joining me, Nathan Sinclaire, as we continue our deep dive into the fascinating and, let's be honest, pretty controversial world of Hydrino technology.
And I'm Emma Greenwood, here to help navigate the complexities of this, well, let's call it a revolutionary theory.
Last time, we took a first look at Dr. Randall Mills's grand unified theory of classical physics, the GUTCP. And we touched on the rather mind-boggling concept of hydrinos, those proposed states of hydrogen with, well, a smaller orbit and lower energy than the ground state.
A concept that has sparked quite a bit of debate, you could say, within the scientific community.
To put it mildly, and today we're going to delve even deeper, focusing on Jonathan Phillips's exploration of this theory, specifically how those hydrinos might actually form.
And Phillips, in his book, lays out a pretty intricate two-step process, almost a sort of atomic dance between hydrogen and a special catalyst.
A dance, all right. Lead the way then. Walk us through it.
So picture this. In the first step, an atom of hydrogen needs to absorb a very specific amount of energy, just enough to push it into what's called a transition state, a very unstable, very short-lived state.
Yeah, it's precarious.
It is, and that's where the catalyst steps in. That's where it gets that crucial energy.
So the catalyst is like what? The key to unlocking the door to a lower energy level?
It's a good analogy, yeah. But here's the thing. What's really fascinating, even mind-boggling, is that this energy transfer, it doesn't involve photons.
Wait, hold on. No photons?
Yeah.
But those are like those little packets of energy, right? How does energy move without them?
Well, that's one of the more controversial aspects of the GOTCP. What Dr. Mills proposes is that the catalyst actually absorbs a trapped photon from the hydrogen atom, leaving behind, as he calls it, an energy hole.
Okay, I'll be honest. I'm going to need some help visualizing this whole trapped photon and energy hole business. It's getting a little abstract.
All right, let's try this. Imagine the electron in a hydrogen atom as, I don't know, trapped in a well. To escape, it needs a certain amount of energy. Now along comes the catalyst, and it has, let's say, a bucket, and it scoops out some of the energy from that well, creating a hole. Now suddenly, the electron has a shallower climb, right? It can escape more easily.
Okay, that helps. So the catalyst is essentially lowering the energy barrier, making it easier for that electron to reach this unstable state.
Got it. What happens next? What's step 2 in this atomic dance?
So in the second step, the electron, now in this unstable transition state, it rapidly falls to a stable, lower energy state, a hydrino state. And as it falls, well, energy is released.
So like the electron is tumbling down a ladder.
Yep.
And with each rung, it releases some energy.
Exactly. But there's another twist. This energy, it's not released as a single photon, not like you'd expect with traditional atomic transitions. Instead, it comes out as what's called Bremsstrahlung radiation.
Bremsstrahlung. Now that sounds intimidating. What's that all about? It's a type of electromagnetic radiation produced when a charged particle, like our electron, is rapidly accelerated or decelerated. Think of it like a car slamming on the brakes, leaving those skid marks on the road.
So the electron is basically braking hard as it falls to this lower energy level. And those skid marks are the Bremsstrahlung radiation.
Exactly. And what's really important is that the GUTCP predicts the specific characteristics of this radiation, which makes it, testable.
Scientists can look for those skid marks to see if hydrinos are actually forming. That's pretty cool.
It is, and it's one of the main ways researchers have been trying to verify the theory. But before we get into all that experimental evidence, let's take a step back. You mentioned catalysts playing this crucial role, right? What exactly are these catalysts, and why are they so special?
They sound pretty important in this whole process.
They are. Catalysts in this context are atoms or molecules that can facilitate this energy transfer. They help the hydrogen atom get to that unstable transition state. And according to the GUTCP, not just any atom or molecule will do, they need to have very specific energy levels.
So like a lock and key situation, only the catalyst with the right key can unlock the door to the hydrino state.
Precisely. Phillips focuses on 2 main types. The first type, called type I catalysts, are atoms like argon and helium. Now, these atoms, they can ionize, meaning they lose an electron, but they do it at very specific energy levels, levels that are multiples of a unit called the Rydberg energy.
The Rydberg energy. Remind me what that is again.
It's a fundamental unit of energy in atomic physics,
Right.
roughly equivalent to 13.6 electron volts. It's the energy needed to ionize a hydrogen atom in its ground state.
Right. Right. So these type I catalysts, they have energy levels that what resonate with the energy needed to bump that hydrogen electron up to the transition state.
That's it. Now, there's also the second type, called type 2 catalysts. These are hydrogen molecules themselves, and they facilitate the energy transfer through specific collision processes.
So hydrogen can actually help create more hydrinos. That's interesting.
Yes, it's called a disproportionation reaction. Essentially, one hydrogen atom steals energy from another, allowing it to transition to that lower energy hydrino state.
A bit of a Robin Hood situation in the atomic world.
You could say that, but it's important to remember all of this is based on the GUTCP, which is, as we've mentioned, still very controversial.
Definitely. So the big question is, have scientists actually found any evidence to support the formation of these hydrinos?
The million-dollar question, and that's exactly what we'll dive into next time. But before we go, there's one more intriguing concept from Phillips's exploration that we should touch on. Fractional hydrogen states.
Fractional hydrogen states. Now, that's something we haven't heard before.
It's a concept closely tied to hydrino formation. Essentially, it suggests that the hydrogen atom can exist in states where its electron orbit is a fraction of the Bohr radius, the typical distance between the electron and the nucleus in a hydrogen atom.
So the electron is even closer to the nucleus than in the ground state.
Exactly. And these fractional states, they're thought to be intermediate steps in the formation of hydrinos. The electron effectively hops down these fractional states, releasing energy along the way.
It's like the electron is taking a shortcut down the energy ladder, skipping some rungs.
That's a great way to put it. And these fractional states are another key prediction of the GUTCP that researchers are trying to verify experimentally.
Wow, okay. This is already a lot to ponder. We've got this two-step dance of hydrino formation, these special catalysts, and now these fractional hydrogen states. It's a lot to wrap our heads around.
It is. But don't worry, next time we'll unpack the experimental evidence that might, either support or maybe even challenge these pretty mind-boggling ideas.
Until then, keep those minds curious. And we'll see you back here at Teolumen Insights for part 2 of our Hydrino Deep Dive. Welcome back to Teolumen Insights. I'm Nathan Sinclaire, ready for round 2 of our Hydrino exploration.
And I'm Emma Greenwood, back to delve into the experimental evidence for this, controversial theory.
Last time we got into a pretty deep discussion of Phillips' work on how those hydrinos might actually form, that whole two-step process. Catalysts, Bremsstrahlung radiation, it was a lot.
It was. But now comes the fun part, right? Actually looking for evidence that these things might actually exist.
Exactly. So Phillips, in his book, really dives deep into the experimental evidence. Where do we even begin?
Well, a good starting point is the idea of excess heat. One of the key predictions of the GUTCP is that the formation of hydrinos should produce excess heat. More heat than you'd expect from conventional chemistry.
Right, because those electrons falling to lower energy levels, they have to release that energy somehow.
Exactly, and that energy often comes out as heat.
So how do scientists actually measure this excess heat? How do they know it's there?
Through calorimetry. Basically, it's a way of measuring the heat produced during a reaction. Phillips discusses various types of calorimetry studies that have been conducted, some by Dr. Mills's company, Brilliant Light Power, and others by independent researchers.
And what have those studies shown? What's the verdict?
It's a bit of a mixed bag, honestly. Some studies have shown pretty significant excess heat, far more than conventional chemistry can explain. And this, of course, is seen as potential evidence for hydrino formation.
Sounds promising.
Yeah.
But I imagine there's some debate around these findings, right? Not everyone's convinced.
Oh, absolutely. There are definitely criticisms. Not all calorimetry studies have produced those clear-cut results. And critics argue that the excess heat in some experiments could be from, errors in measurement, or problems with the experimental setup, or maybe some other factors completely unrelated to hydrinos.
So it's not a slam dunk when it comes to the calorimetry data.
Not quite. And even Phillips himself, he's pretty critical of some of the calorimetry studies out there. The ones he doesn't find, rigorous enough. He really emphasizes the importance of accurate measurements, proper calibration of equipment, and those robust experimental controls, all to rule out any alternative explanations.
Well, that sounds like good scientific practice in general.
Definitely. And he puts a lot of emphasis on a specific type of calorimetry called Bohm calorimetry.
Bomb calorimetry. Sounds intense.
It is. It involves a very rapid and controlled release of energy, almost like a miniature explosion happening in a sealed container.
Okay, so if hydrinos are forming in that kind of environment, the excess heat should be pretty noticeable, right?
Exactly. And Phillips points to some Bohm calorimetry studies by BLP that have reported very high energy releases, like way more than conventional chemistry can explain.
Interesting. So we've got calorimetry as one potential line of evidence. But are there other ways to detect hydrinos, other things scientists are looking for?
Absolutely. Another key area of investigation is spectroscopy. That's where you analyze the light emitted from a substance to get information about its composition and those energy levels we keep talking about.
Right, like those skid marks we discussed earlier, those unique signatures of Bremsstrahlung radiation. Scientists can actually look for that, right?
They can. And the GUTCP predicts that this radiation should fall within the extreme ultraviolet, or EUV, part of the electromagnetic spectrum.
EUV, wow, that's pretty high energy stuff.
It is. You need specialized equipment to detect it.
So have researchers actually found any evidence of this EUV radiation? Like coming from reactions that are thought to produce hydrinos?
Yes, actually. Dr. Mills and others have conducted studies using EUV spectroscopy, and they've observed specific bands of radiation that seem to match the predictions of the GUTCP.
Hold on, though. How do they know that those EUV bands are specifically from hydrinos? Couldn't it be something else going on in the experiment?
That's where those control experiments come in. Researchers compare the EUV spectra of reactions with all the right ingredients for hydrino formation to control reactions where one or more of those ingredients is missing. And what they found is that those specific EUV bands, they only show up when all the conditions for hydrino formation are present.
Okay, so that seems like pretty strong evidence.
It's definitely compelling, but again, it's important to note that these findings are still being debated within the scientific community. It's not a done deal.
Now, you mentioned earlier that spectroscopy is also used to analyze the energy levels of atoms. Does that play a role in hydrino research as well?
It does. Remember we talked about the Balmer series last time? That set of spectral lines you see when you analyze the light coming from excited hydrogen atoms?
Right, those specific wavelengths of light that hydrogen emits when its electrons are jumping between energy levels.
Exactly. And the hydrino hypothesis, it predicts that, under certain conditions, those Balmer series lines can start to behave in unusual ways.
Unusual how? What kind of unusual behavior are we talking about?
Well, they can become more intense, or even inverted, meaning the relative intensities of the lines change in a way that's not expected based on conventional physics.
And this unusual behavior is linked to the presence of hydrinos.
That's the idea. The presence of hydrinos is thought to influence the energy levels of the surrounding hydrogen atoms, leading to those unexpected changes in the Balmer series.
Has anyone actually observed this happening?
Yes. Phillips cites some laboratory experiments where researchers have observed this inversion of the Balmer series lines, specifically under conditions thought to favor hydrino formation.
Okay, so we've got calorimetry showing excess heat, EUV spectroscopy detecting those predicted radiation bands, and now this unusual Balmer series activity. It's starting to feel like there's a lot pointing towards hydrinos.
There's definitely a growing body of evidence, that's for sure. But we have to remember this is still an area of active research, and more work needs to be done to confirm these findings, address the concerns of the critics, and ultimately determine if hydrinos are truly a real phenomenon.
Now, with all this talk of catalysts and spectroscopy, I almost forgot. Those fractional hydrogen states we briefly touched on last time, what's the latest on those?
Yes, those fractional states. They're thought to be those intermediate steps in the formation of hydrinos. Remember, the GUTCP proposes that the hydrogen atom can exist in states where its electron orbit is a fraction of the Bohr radius, that typical distance between the electron and the nucleus.
Right. So the electron is even closer to the nucleus than in the ground state. And these fractional states are like stepping stones on the way to forming a hydrino.
Exactly. As that electron cascades down through these fractional states, it releases energy. And that could explain some of the observed spectroscopic and calorimetric phenomena we've been talking about.
It's all starting to connect. But I have to ask, if these hydrinos are real and we can actually harness their energy, what are the implications? What could this technology do?
The possibilities are, well, pretty mind-boggling. Hydrino technology has the potential to be a clean, abundant, and incredibly powerful source of energy. Imagine a world powered by devices that essentially mimic the energy production of the sun, but without all that radioactive waste from nuclear power.
It sounds almost too good to be true.
It does, but that's what makes this research so exciting. It's pushing the boundaries of what we understand about energy and matter.
We've covered so much ground today. Calorimetry, spectroscopy, fractional states, even the potential applications of this technology. It's a lot to absorb.
It is, but I think it's safe to say that Phillips has presented a really compelling case for hydrino research, even if it challenges some of our most fundamental scientific assumptions.
Well, this deep dive has definitely left me with more questions than answers, which I guess is a good thing. It sparked my curiosity, that's for sure.
And that's what Teolumen Insights is all about. Exploring those frontiers of knowledge and encouraging you to ask the big questions.
Thanks for joining us on this journey into the world of hydrinos. Until next time, keep those minds curious. Welcome back to Teolumen Insights. I'm Nathan Sinclaire.
And I'm Emma Greenwood, ready to wrap up our deep dive into hydrinos.
We've covered a lot of ground so far, from the theoretical underpinnings of hydrino formation to those experimental results.
Right, we talked about catalysis, spectroscopy, even those fractional hydrogen states.
It's been quite a journey, but there's one more aspect of Phillips's exploration that we need to touch on before we wrap things up. Continuum radiation.
Continuum radiation, it plays a key role in the experimental evidence for hydrinos.
Can you remind me what that is again? It came up briefly when we were discussing Bremsstrahlung, but I'm still a bit fuzzy on the details.
Of course. So continuum radiation, it's basically a broad spectrum of light emitted over a range of wavelengths. It's different from those discrete spectral lines we usually see with atomic transitions. Instead of those distinct bright lines, it's more like a smooth blend of colors, if you will.
Okay, that makes sense. So how does this continuum radiation tie into the whole hydrino story?
Well, the GUTCP, it predicts that the formation of hydrinos should produce a very specific type of continuum radiation, one with a sharp lower edge.
A sharp lower edge. What does that mean exactly?
It means that the continuum radiation, it suddenly cuts off below a certain wavelength. Basically, you see this kind of cliff in the spectrum.
Interesting. And this sharp edge, it's somehow related to the hydrino formation process.
Exactly. The theory predicts that the energy released during hydrino formation, it can only produce photons up to a certain energy level. That level is determined by the specific energy difference between that initial hydrogen state and the final hydrino state.
I see. So any photons with energies higher than that threshold, they just can't be produced, which is why the spectrum abruptly ends at that point, like hitting a wall.
Precisely. And this sharp lower edge, this sudden cutoff, it's another key prediction of the GUTCP, another thing researchers have been looking for in their experiments.
And have they found it? Have they seen this sharp edge in the spectrum?
Yes, Phillips cites a number of studies that have. They've observed continuum radiation with that sharp lower edge in various experimental setups involving hydrogen and catalysts.
So it's like those EUV studies we discussed earlier, but instead of looking for specific bands, they're focusing on this abrupt cutoff in the spectrum.
Exactly. And the wavelengths of those lower edges, they seem to correlate with the predicted energy levels of hydrinos, adding another piece to the puzzle, so to speak.
Wow. Okay. So we've got excess heat, those unusual Balmer series activities, the EUV bands, and now this continuum radiation with a sharp lower edge. It's a lot of different lines of evidence, all seemingly pointing towards the possibility of hydrinos.
It is. It's quite a compelling body of evidence, even if it's, still being debated and scrutinized within the scientific community. It's not a closed case by any means.
Right. I know there is still a lot of skeptics out there, people who just aren't convinced by this whole hydrino hypothesis. What are some of their main arguments against it? What are the doubters saying?
Well, a very common criticism is that the GUTCP itself, the theory underlying all of this, it's based on a non-standard interpretation of quantum mechanics. And that makes a lot of physicists, well, uncomfortable, to say the least.
So they're essentially questioning the very foundation of the hydrino idea.
Yeah, you could say that. They argue that the GUTCP makes predictions that contradict well-established principles of quantum mechanics. They say there's no need to invoke these new exotic states of hydrogen.
So it's a really fundamental disagreement. A clash of interpretations, you could say.
Exactly. And then there's the experimental evidence itself. Some critics say that some of it, particularly the calorimetry data, it's open to interpretation, that there might be other explanations for those results besides hydrinos.
Right, like those potential measurement errors or other factors that could be influencing those heat measurements. We talked about that earlier.
Exactly. And another point the skeptics bring up is that despite years of research and development, There's still no commercially viable hydrino-based technology out there. No products you can buy, no power plants using this stuff. And for them, that's a sign that the theory, well, it might just not be practical.
So they're basically saying, show me the money. If hydrinos are real, where are the working devices? Where's the proof in the pudding?
That's one way to put it. But it's also important to remember that scientific breakthroughs, they often take time to translate into practical applications.
That's true. Think about fusion power. It's been this tantalizing possibility for decades, but we're still a ways off from having fusion reactors powering our homes.
Exactly. And the field of hydrino research, it's still relatively young. It's entirely possible that with continued research and development, we might one day see those hydrino-powered devices become a reality.
It's certainly something to think about. Now, amidst all this scientific debate and the experimental uncertainty, there's this bigger question looming. If hydrinos are real, and we can harness their energy, what could that mean for humanity? What are the implications?
The implications are pretty profound, to say the least. Hydrino technology has the potential to revolutionize how we produce energy. It could offer us a clean, safe, and virtually limitless source of power.
Imagine a world free from fossil fuels, a world where energy scarcity is a thing of the past. It would transform everything: transportation, manufacturing, our daily lives.
And it goes beyond Earth, too. The implications for space travel are incredible. Hydrino-powered spacecraft could travel vast distances, opening up new frontiers of exploration. We could even potentially reach other star systems.
It sounds like something out of science fiction, but it could actually become reality.
It's a very tantalizing glimpse into a future where energy is no longer a constraint, but a catalyst for progress and innovation.
It's certainly a lot to ponder. This deep dive into the work of Jonathan Phillips and the world of hydrino technology have been fascinating, to say the least. It's challenged our assumptions about physics, about energy, and it's opened our eyes to the possibility of a very different future.
And whether or not hydrinos ultimately prove to be a viable source of energy, well, the very pursuit of this knowledge has already pushed the boundaries of scientific understanding, and that in itself is quite a remarkable achievement.
From Teolumen Insights, thank you for joining us on this incredible journey into the uncharted territory of hydrino science. Keep those minds curious and keep those questions coming, because the quest for knowledge, well, it's an endless adventure.